So for the gradient and level curve, so let's consider the idea that f is differentiable at a given point, and number one, the gradient at the given point is not equal to the zero vector. Then the gradient vector is normal to the level curves through the point x, y. So that is, in other words, because again, the derivative which gives us the tangent vectors are going to be orthogonal to this and to this gradient vectors. You can see this from the picture here. See how the tangent vector is orthogonal to the gradient vector at a given point, in this case AB. For the second situation, we choose another point C, comma D, E, comma F, whatever point. So that's always true. The tangent vector and the gradient vector are all orthogonal. So this is very important, because when we see this setting in the space in 3D, that's going to be very important information in equations of planes. Well, let's have a look at one example to see this idea well. So consider the function z equals to x squared plus 4y squared. Number one, or letter A rather, let's describe the level curves for this function and then sketch the level curve for c equals to 8. Well, so let me replace. Let's replace x squared plus 4y squared equals to z rather equals to 8. Okay, so we're replacing our dependent variable with a number to find out what's the height, or rather what's the curve, what's the level curve. All right. Okay, let's observe this equation. Well, what do we have? Variable squared, both positives, right? So what does that equation represent? What was that? It's an ellipse, right? Because both squared, they're all positive, but the coefficients are different. Divide by 8. All right, so that means x squared over 8 plus y squared over 2 equals to 1. That is an ellipse where the x-intercepts are plus or minus the square root of 8, or 2 root of 2 comma 0, and the y-intercepts are 0 comma roots of 2. Right? Oh, plus or minus. Don't forget that. And we need this to graph this ellipse, of course. Okay, so they're asking us to find the gradient at the given point 2 comma 1 and sketch it on the level curve. Find the slope of the tangent line at the same point and verify that the gradient is orthogonal to the tangent vector at that point, which is what we have in the definition. So this exercise is number one, to see this in action and to verify the orthogonality of the two given vectors, the two vectors that are involved. So number one, let's find the gradient. Nabla of, well, let's define this as an f if you want, or this is z, right? That equals the partial with respect x, that is 2x, the partial with respect y, that's 8y, okay? And evaluating the gradient at the point, what's that? 2, 1, that equals 2 times 2, 8 times 1, which will result into the vector for 8, okay? The vector for 8. All right. So what else are we going to do with this? Well, they're asking us to find the tangent vector. Okay, so to find tangent vectors, well, for this particular case, it's going to be a little tricky, because how do we get tangent vectors? Using the derivative, right? But in this case, we don't have a vector valued function. We don't have a parameterization of this ellipse. Even though we can come up with something, it's not necessary. I'm going to take a different approach. So instead, I'm going to use the implicit differentiation that we learned in the previous lecture, or well, sometime last week, I believe. Yeah, I think it was last time, right? So, well, how do we find How do we differentiate this implicitly? Remember, that is negative the partial of f with respect x divided by the partial with respect y. What we wished we knew back in Calc 1, right? Just the quotient of the partial derivatives. So, and why are we taking this approach? Because we already have that information here. That is negative 2x over 8y. That equals negative x over 4y. All right. Now, we need to evaluate this derivative at the point 2, 1, because that's going to give us the components of the vector, of the tangent vector, right? Because derivative means tangent, but we want a tangent vector, okay? So, df dx at the point 2, 1, that equals negative x, which is negative 2 over 4 times 1, that is negative 1/2. All right, but how are we going to turn this into a vector? And you might ask yourself. So again, we wish we had a parameterization of the given function, but we don't have it. And coming up with a parameterization is just going to take forever. So again, let's go back to pretty much day 1 when we define a vector v. Don't we define vectors as terminal minus initial, terminal minus initial? Isn't that just finding the differences between 2x values and 2y values and 2z value depending on the component? Well, so that is essentially delta x, delta y. But you might ask yourself, where do we get that delta x and that delta y? Oh, that's value of the slope. The value of the slope, which is the rate of change, which is the change in the x and the change in the y. Isn't that number in the numerator representing a delta y, a change in the y, a change in the x? So that's going to give us the components of the vector. But wait, even crazier here. So we have a negative number. Are we going to give the negative to the 1 or the negative to the 2? It doesn't matter. You'll see when we get the picture. So it's either negative 1, 2 or 1, negative 2. Again, one vector is going to go in one direction, the other vector is just going to go in the opposite direction, but it's still a line, in the same tangent line that contains that vector. Okay, let's plot the ellipse. Let's plot the ellipse. So that is 1, 2, 1, 2, 1, 2, and 1, 2. Okay, let me draw the ellipse as best as possible. Well, we're going to use the intercepts we obtained earlier. So 2 root of 2, that's roughly a little bit more than 2, right? And root of 2, it's 1 point something. So I'm going to go like this. I'm going to estimate like this. All right? So that's going to give us the ellipse. So let's go to the point 2, 1. All right? The point 2, 1, which will be this point 2, 1. All right? That is this point. I don't know why it's doing this. Anyway. There we go. No. Okay, so that's our point, 2, 1. From there, check this out. From there, I'm going to plot, number 1, the point, or rather the vector, with components negative 1, 2, that is negative 1, 2. Did you see how this vector is tangent? And also the other vector, 1, negative 2. I'm going to use a different color for this. Like this. Whoops. Now, from this same point, 1, 2, I'm going to plot the vector, the nabla vector, the gradient vector, that is 4, 8. right? That is nabla f, which is 4, 8. Now, from the picture, well, because I tried my best to make them look perpendicular, for sure these two vectors are orthogonal, right? But the picture is not enough. We need to show this algebraically. Again, how do we show that two vectors are orthogonal? The dot product equals to 0. Let's verify that. Okay, is it true that nabla of f at 2, 1 dotted with v equals to 0? Let's find out. Okay, the vector 4, 8 dotted with the vector, and you can do either one of these two. You don't have to do both, all right? That's 1, -2. Okay? So, oh wait, I got this reversed. It's 2, -1, and 2, -2, 1. Otherwise, it's not going to work. 2, -1. I'm going to do the first one. 2, -1. 4 times 2 equals to 8. 8 times -1, -8. Oh, 8 minus 8, 0. And that's how we show the orthogonality of the vectors, which is this 90-degree angle, right? How is that going to be important? You'll see these level curves now being placed in 3D surfaces. You'll see. Okay, so let's have a look at the last piece of information. That is, for functions of 3 variables, we will now find the gradient, find the maximum, the direction of maximum increase. Again, we're going to have this time a function of 3 variables. All right. So whatever you did back with functions of 2 variables, just do it 1/3 time for the third variable. Have a third term. Number 1, the directional derivative. It's going to be simply the partial with respect x, the partial with respect y, the partial with respect z, dotted with a, b, and c, where a, b, and c represent the components of the unit vector, which is the direction in which we go. I know at the beginning of the section we denoted this vector with u1, u2. Well, technically we should use u3. Doesn't matter. I mean, in the end, as long as you know for sure this vector is a unit vector, use your favorite letters. That's fine. All right. And the gradient will be simply a vector that contains the partial derivatives with respect x, with respect y, and with respect z. All right. The same properties of the gradient are going to be extended to vectors or to gradients in the space. That is, number 1, the directional derivative, which is the dot product between a unit vector and the gradient. If it's the 0 vector, then the gradient must be 0 for all these vectors. And same, the direction of maximum increase is going to be given by the magnitude of the nabla vector evaluated at the point, and minimum increase, just take the opposite inside. That's all. All right. Let's do one example. And for this simple example, actually, I forgot to change this this function. I wanted to make it easier. Let's get rid of this radical. Yep. So that is okay. That's so we can get a quick gradient here. So find the maximum rate of change for this function, x squared plus y squared plus z squared at the point 3, 6, -2, and the direction in which it occurs. Okay, so number 1, nabla f, okay, that is partial with respect x, partial with respect y, and partial with respect z. That is 2x, 2y, 2z. Right? Very quick and simple partial derivatives. Now we need to, okay, so before we can get the maximum rate of change, so first we need to know in which direction it's going, because that rate of change will be given by the magnitude of the vector that gives that direction. All right? So let's evaluate. nabla of f at the point 3, 6, negative 2, that is 2 times 3, 2 times 6, and 2 times negative 2. So that's going to give us the vector 2 times 3 that equals to 6, 12, and negative 4. Alright? Okay. What is that maximum rate of change? So maximum rate of change, that is going to be this vector with the magnitude of the vector we just obtained. That is 3, 6, negative 2. That is the magnitude of 6 squared plus 12 squared plus negative 4 quantity squared. So that's going to give us a big number. So 36 plus 144, that's 150, 180, 196. Which is a nice number, by the way. That's 14. All right. Okay, let's talk about this exercise because, I mean, pretty simple partial derivatives, pretty simple computations, but what are we really doing anyway? So, for the gradient, for the four functions with two variables, so the easiest way to visualize that, it was by having that surface representing a hill, you know, or a temperature profile, that to tell us in which direction to walk, where it's steeper in the hill. However, this is technically a function of four variables. Can we visualize the four dimensions? Not really. Okay, so let's think of this four variables, yes, three independent, one dependent, as a function, say, temperature. Or pressure. I don't know. So what are this function will give us the different temperatures at different points. So the input is our triple, that is a point on the surface, and that fourth variable, which is the dependent variable, will be a physical quantity. In this case, temperature or pressure. So for instance, in this case, if this were temperature at a surface, if we go in this direction, this is the direction where it gets hotter on the surface, and it looks a lot like, like a sphere, right? Looks like it's a spherical surface. Now, in which direction should we go in order to cool down quickly? Negative 6, negative 12, and positive 4. So in the opposite direction, right? So that's how we can visualize gradients and directional derivatives for three variables. All right, so this is the end of